So for memory, I'm just going to start off with a little bit of a high-level introduction. I do see someone typing a question, and I'll address that if once I see it. But start off with memory. Let's just talk a bit about the high-level stuff because it's important to understand the context, why we're even looking into main memory. So as you have been doing with VMAL, you've been programming pretty much only with registers. And you don't have very many. And depending on how you implemented the multiplication algorithm, you probably started to get into the problem where you were using maybe 8 to 10 registers, kind of pushing the limits. And you could imagine that you know doing anything more complicated than that, you'd end up running out of registers. So how do you get around that? Well, the idea here is you add a massive amount of main memory in some capacity, and you need the main memory needs to work in some specific manner, and that manner ends up actually just being like an array. And there's a really good reason for that. It's actually because arrays, the data structure of arrays is modeled after how the memory is structured. And so literally our goal when doing main memory is to implement an array. That's basically it. We want to be able to specify an index where we're writing the data, where we can write a data to, and also read data from. But we're going to do it in this potentially bizarre manner where we're going to be reading and writing on the same, like the data that we're reading and writing is going to be on the same bus going in 2 directions. This is sort of a new concept for this class, but it's not too complicated. And I mean, yeah, that's basically it. Our goal is to implement in hardware an array. So for this, we're pretty much going to be using D-latches. Because D-latches are much easier to use than SR latches or most other memory structures. And again, the reason we want to use a D-latch is because we're going to want to have this data line coming in. You know, maybe it's n bits, and we want to be able to just write whatever this is. And D-latches, obviously, they just accept a data input, and then we'll just store whatever that data is. It's perfect for this sort of scenario so that we can write exactly what we want to write and not have to deal with this weird S and R stuff or a different form of input for a different type of memory latch. And so, well, the first thing that we have to figure out is how to store multiple bits together, right? Because a D-latch only stores a single bit. And like on circuitverse, you can just increase the bit width, but that's not really realistic, right? There has to be an actual circuit going on. So how can we go ahead and go from an n bit, let's just say 4-bit for simplicity, how can we go from a 4-bit input and essentially make a 4-bit D-latch so that it stores 4 bits at a time? Well, let's just split apart the bits. So I have my bus coming over here. Let's just take the 0th bit here. We'll take, actually, so notation wise, I should just do this. So we'll take the 0th bit here, the 1st bit here, the 2nd bit here, and the 3rd bit here. And then what we can do is just put a row of D-latches. So each D-latch here is going to be responsible for holding one of the bits of the number. And that's pretty much it, right? And all we need to do now is make sure that if we write to one of these location, if we write to this one, we also want to write to every single other one, because we want to make sure that the value of this thing, which is called a register, we want the value of this thing to be consistent with the input. We don't want to be able to modify individual bits. We want to modify the whole value of this register at once. So essentially all we need to do there is connect up the clocks. And so we got our D-latches here, and then we can go ahead and just connect up the clock inputs. We'll say the clock inputs are right here. And we can just connect these up like this. And that's pretty much it. And then we also have your outputs here. And if you wanted, you could easily recombine these together into some Q bus. So this is a 4-bit input and Q. So this here is known as a register. And essentially, you take a 4-bit number and you can write it into the register, and then you can read that output. It works just like a D-latch, it just stores a larger number. And the reason it's useful to talk about these registers is because it helps to simplify once you get to more complicated things. But the idea here is if you want to increase the data width, you just sort of add components horizontally and then just connect up the control logic to each of them. So that way, let's say you have 2 memory components that each can handle 4 bits. Like let's say I was trying to make this 4-bit register, but all I had were 2-bit registers, right? So if I only had 2-bit registers, all I need to do here is put 1 2-bit register here, 1 2-bit register here. Then I can have my 4-bit line coming in here. And then instead of just taking off the individual bits here, I can just take off the upper 2 bits and the lower 2 bits. Store the upper 2 bits in here, lower 2 bits in here. Connect up the clocks as usual. And that's it. Right, now we're storing 4 bits. So that's an important concept when you're dealing with memory. To increase the data width, you just add stuff horizontally and connect up the way that you control it. And obviously, you split up your data into multiple chunks, and you feed each chunk individually into each of the units. Okay, so now that we have an ability to create a component that can store an arbitrary number, well, now our goal is to make an array. So we need to have multiple locations that we want to store things. And, well, I'll make some specifications for the analogy. In an array, we call a location an index. In memory, we call it an address. So that's it. So when we say an address, it just means an index into this large array that we call the memory. For now, we're going to assume that the memory is word addressed, meaning that it essentially works exactly like an array. So let's say if we have an array of 4 numbers, this first location here would hold a 4-bit number, or let's say, I don't know, let's say we're doing a memory with 4-bit data. So at the first location, we would have a 4-bit number. The second location, we have a 4-bit number, and so on. And for however many locations we have. So, but the data width will be specified in any sort of problem. So let's say here we want to implement something with a 4-bit data bus and a 2-bit address bus. So I'll start off with my data here. And now here I'm just going to use a register. Sometimes in the problem it'll specify to use D-latches or something. You just need to be flexible. But for simplicity's sake, just for understanding how to do the addressing logic, I'll just use registers. So now, in order to add locations, I'm going to start doing vertical stuff. And someone made a comment about endianness. It doesn't really end up being a problem if you're doing word addressing. That really becomes a problem if you're doing byte addressing, which is what most modern computers do. But if you don't know what that comment was about, don't worry about it. We don't really cover that in this class because it doesn't really end up being a problem for most people. But if it is, it's something that you definitely. It's not too complicated. So yeah, so in order to add locations to our array, we're going to do so vertically. And that's just the general pattern. If you want to increase the data, you go this way. If you want to increase addresses, you go this way. And that's just sort of a conceptual model, makes it a little bit clearer. So right now I'm just creating 4 of these 4-bit registers because we have a 2-bit address. And so you have to keep in mind, 2-bit address doesn't mean we have 2 locations. It means we have 2 bits worth of a binary number to address locations. So here we'll call this location 0, 0. We'll call this location 0, 1, 1, 0, and 1, 1. And if you convert these from binary into decimal, that's just 0, 1, 2, and 3, which would be the indexes of an array. And this is why arrays are indexed. They start at 0, is because it's literally just a binary number. And if you don't start at 0, you're just wasting a number, right? If we started our addresses at 1, well, we wouldn't be able to have this location 0, and it's just a waste. We're just, sort of just wasting an address for no reason. Except for certain programming languages, which do have arrays indexed from 1, but those are usually higher level. So yeah, so this right here is maybe a little bit weird. It's just to simplify the drawing. All I'm doing here is I'm connecting up this D line to the D input of all of these registers. And then let's say the Q output is over here on this side, just for simplicity. Okay, so now we'll just focus on the write aspect of this. So we want to be able to write to one of these locations based off of an address that is passed in. So we'll have right here, let me actually move this over a little bit. So we have right here coming in a 2-bit address bus. So here there's going to be like an A1 and an A0. And if I look again at this, this would be A1, this would be A0. So now, how can we, based off what this address is, figure out where we want to write? Well, keep in mind, these registers have clock signals. And the clock signal, whenever it's 0, so if I just pass in a 0 to here, it's just going to hold that information. It's not going to do anything with it. The only time that anything's actually going to be written is if we send a clock signal to 1. And so if we want to write to one of these specific locations, all we need to do is send a 1 to the location that we want to write to. And then it'll take that data and overwrite whatever the existing data is in that register. So how do we do that? So we need to go from a binary value to sort of just pointing out exactly which register we want to write to, right? So like if we and make sure you mute yourself if you are not saying anything. Sorry about that. Yeah, so we need to, let's say if this is 0, 0, we need to somehow send a signal here. If it's 0, 1, we need to send a signal here. How can we do that? Well, essentially what we're trying to do here is decode binary. We're trying to go from a binary signal to knowing what number it represents. And so here we'll use just a binary decoder. And it does essentially exactly what I just said we want. So it'll take a 2-bit binary input, or n bits. It doesn't really matter how many bits it is. And then it'll split it up into 4 different outputs in this case, because there's 4 different 2-bit binary numbers. And it'll just tell us what binary number was passed in. So if I pass in 0, 1, all of these lines are going to be 0 except for this one. And it's just going to tell us, hey, that's the one that you want to write to. And making this is super, super easy. It's like you can actually use a binary decoder to make a multiplexer. So binary decoders are actually more simple than a mux. So here, if I have my A1 and A0, all a decoder is just a bunch of different AND gates. So here, we'll take these two, invert them both, pass it through an AND gate, and that's the 0, 0 output, right? Because when this is 0 and this is 0, this will be a 1. Otherwise, this will be a 0. And then if we want the 0, 1 input, that'll just be this. Right? So when I pass in a 0 and a 1, this will turn on. Otherwise, it'll be 0. And that's literally just it. You just sort of go through each of the min terms and add an AND gate for that. And there you go. That's a binary decoder. Very, very simple. But usually we can just draw this out because otherwise it would get a little bit hectic. So now, well, I mean, we have the signal, right? We could just pass these directly into the clocks, and that way it would write to the right location. But as with pretty much everything else in a CPU, we want it to be synchronized with the clock, because if it's not synchronized with the clock, things are just going to happen whenever they get the input signal, which is not good. It's very, very difficult to figure out what's going on if you're just constantly, if the CPU is just constantly doing something as soon as it gets an input. So here we want to add a clock signal to control whether or not we're actually doing anything. So here, when this global clock signal is a 0, we're not doing anything. We're not reading, we're not writing. We're just going to be sitting still, storing all the values. This would just be like the memory is just, this array here just not doing anything. It's just sitting in memory. So, but when it's a 1, well, we might want to write, we might want to read. So what we're going to do is we're going to add another line called the, let's see, how is this? I think it's not read write line is what we normally call. So this is a little bit weird syntax, but essentially all this means is when the read, not read write line is a 0, then we're, let's see, reading. And when it's a 1, we're writing. And might have this backwards. It might be read, not write, in which case this would be flipped around. But the idea here is if not r equals 0, that means r equals 1, so you're reading, but then write would be 0, so you're not writing. And then on the other hand, if not r is 1, that means r is 0, and w would be 1. So that's all this is denoting, is that if it's the opposite. So if it's 0, then it's doing one of the two. If it's 1, it's doing the other. Just a little bit of a weird syntax. Okay, so now, in order to write here, we want this line to be a 1, and we want this clock to be a 1. Otherwise, we don't want to be doing any writing. So let's just go ahead and AND these two signals together, right? Because that's what you use. You use an AND gate if you want two things to be 1 simultaneously. So here, I'll just pass both of these into an AND gate. And now I have a signal that is going to be a 1 when I want to write something. So now, if I take this signal here, remove that, and I just sort of wire it up. Actually, I should probably do this a little bit backwards. Right here. So now if I go ahead and put some AND gates here, and I use one of the inputs coming from this clock input, so now, if, let's say I have another input here, well, no matter what, if this line here is a 0, all of the inputs to the clock are going to be 0, because 0 and anything is just 0. However, when this transforms into a 1, well, if any of these other inputs here are a 1, then it'll be, 1 and 1 will be 1, and it'll write to that location. So now if we just take the outputs of our binary decoder and wire them up to these inputs here, we're done for the write portion of the memory. So let's walk through this real quick. So let's say my address is 0, 0. Okay, so I pass in a 0, 0 here. So that'll make this wire a 1, this wire 0, this wire 0, and this wire 0, right? Because the binary decoder identifies which binary number I passed in. So that's a 1. So that's 0, 0, so it'll pass this wire as a 1. So now let's assume, the clock is going to be 0, and we've already set this to 1 because we know we want to write. So the clock being 0, so 0 and 1, that'll just be 0. And so we're passing 0 to all of these, and so all of the outputs of these AND gates are going to be 0, and we're not doing anything we're not writing anything. However, the moment we change the clock to 1, well, 1 and 1 is 1, so it'll change this to a 1. Then it'll pass a 1 to all of these. Well, for these bottom 3 AND gates, it'll do 1 and 0, which is just 0. So it's not going to do anything, it's not going to write anything to these bottom 3. However, this one has a 1 here, so it'll do 1 and 1 is 1, and it'll write this data to this location, which is exactly what we wanted. We wanted to be able to pass in the location to write, and then write to that location. And so this is literally all of the logic for doing writes. And this is indefinitely extendable to as many bits as you want. If you want a 3-bit input here for the address, you just use a 3-bit binary decoder and you wire it up exactly the same. You'll just have more registers going vertically. And so on. You just can keep adding bits, and it doesn't really add any sort of complexity. Obviously, there's added complexity inside of the binary decoder, but that's simple enough to make that, you know, it's easier to just draw it as a box. So is there any questions so far about how the right portion of memory is going to work? All right. So now we have to move on to the read portion. And the read portion gets a little bit bizarre because we want to essentially end up reusing this D line. And so one thing to point out here is that these D latches constantly output. So this is constantly outputting its current state. You know, these registers, if I said D latches, but it's just like a D latch. They just output their state constantly. There's no ability to turn that off. And so if we are constructing memory out of D latches or registers, you have to add some logic to the output queue here to control whether or not it's going to use that output, right? Because we somehow have to choose between each of these outputs here. But if you remember back from combinational logic, whenever you have many choices and you want to choose one of them, what sort of component does that tell you to use? Exactly, a mux. Because a mux essentially will just take in multiple inputs and some sort of selector lines to select which input, right? And that's exactly what we're doing here. We want to be able to select based on using this address. So like, let's say this is 0, 1, and now we're reading. So if this is 0, 1, we want to take the output of this one here and output it onto the D line. And so, yeah, this is literally going to be our selector line, and we'll be selecting between this. The problem now, however, is that we have multiple bits to deal with. Now, in something like circuit verse, we could just make a mux with a 4-bit data width. So we would just have essentially a mux here that would just multiplex between 4-bit binary numbers as opposed to single bits, right? And that would just work exactly the same as a normal mux, right? So we have I0, and then we would pass our address in, and then this would just come here as I2, I1, and so on. And then we could just select which of these 4-bit numbers we want. However, we want to make sure that you understand the nuances behind that. So we'll have to break apart these values here into their each of the 4 bits. So let me go ahead and do that for one of these. So we have Q0, Q1, Q2, and Q3. And we have 4 different wires coming out here. And don't worry, I mean, also with the fact that the class is online now, we're not doing a whole lot of, we're trying to limit the amount of drawing. But even if you did have to draw this, you're not going to have to draw like every single line painstakingly. You can sort of do a pseudo drawing that just indicates that you understand what needs to happen. So we have these 4 bits here, and we have these 4 bits, you know, for every single one of these. So we have essentially 16 lines, and we need to choose the correct lines to output. So let's say here, we'll first just put down a mux, because obviously we want to use a mux, or muxes here, actually. And now we need to figure out what we're going to pass into here. So we already know that the address essentially is going to get passed in into here. Let me move this back here a little bit. So I'm going to take this address and just bring it all the way around over here. Keep in mind this is 2 bits, so it's actually 2 selector lines coming in. So we have I0, I1, I2, I3. So we have 4 inputs here, and we don't want to just take each of these 4 bits and pass them all into the same mux. That's very important. That would be incorrect, because if you do that, You're saying that you want to choose between the bits inside of this register. But keep in mind, this register is supposed to hold a single, in this case, 4-bit binary number. If it would be larger, it could be 32 bits, 64 bits, whatever. It's holding a single number. You do not want to break those bits apart. If you pass in the individual bits all into the same multiplexer, you're de facto trying to choose between the bits of that number. You're trying to say, okay, well, I store this number in my register. Now I'm going to choose to output this one bit. That doesn't really make any sense. You want to output this whole number or the number from a different location. And so you don't want to pass in all the numbers, all the bits of the same number. You want to pass the same bit value from every register into the mux. So here I'm going to take the Q0 output of here and pass it into I0. Here I'm going to take the Q0 output of this register and pass it into I1 because it's in location number 1. I'm going to take the Q0 output of all of these and pass it into the multiplexer. That way, what you're saying is, okay, well, I have 4 numbers stored here, right? I have this number, this number, this number, and this number. Well, in order to output only one of those numbers, I have 4 choices for Q0. I'm going to choose one of them. I have 4 choices for Q1. I'm going to choose one of them. And so you're actually going to have a multiplexer. And here I'm just going to also just sort of draw it with overlap and say that the selector lines are going to be connected right here. That's what that dot means, and I'm just passing it through. So here now I would take all the Q1 outputs and wire them up to this one here. So whatever Q1 is, that would come over here. And yes, I understand this is getting hectic. I won't draw the full thing, but this is just to get an idea for why and how you need to hook these stuff up, because we will be asking questions about this. So hopefully you can see here that I'm taking all the Q1 outputs of the registers of all the different locations and passing them into 1. So essentially this mux here is going to choose our final Q0. This mux here is going to choose our final Q1. And really, we want to pass these selector lines to each of these muxes because we want to select the same input from each of these. So if we're selecting I1 from here, we want to select I1 from here and from the other 2 muxes here, right? We're going to need to have 4 because we have 4-bit data. So we would have 4 registers. So we either want to select I0 from all of these. If we select I0 from all of these, well, that's going to be all of the bits from this first register. So the output of these multiplexers is going to be the first number. So any questions about this so far? All right. So now this is getting into sort of the electrical aspects of memory, and this is just the way that it's usually made. The problem with memory is that it's usually so massive, and it would get complicated to handle if memory had both an input and an output. And that also goes back to how the CPUs are usually designed. Instead of having wires essentially, or buses connecting every individual component, like let's say you have the CPU, you have the main memory, and then you have like, you know, PCIe stuff in a normal computer. Let's say you're connecting your graphics card. So instead of having to interconnect everything together, usually there's just a single bus that you pass everything on, and everything has to share that. And so it's a little bit difficult. You don't want to wire an input and an output going to and from the CPU to the memory. You want to just have one bus that you can use 2 ways. And so what we need to do here now is pass this Q input, this Q output here, through the D line. So this D line here is going to be both our input and our output. If we're writing, we're going to accept an input through D. If we're reading, we're going to output through D. And to do that, we need to add some special components to the end of this to prevent this output from clogging up the D bus if we're trying to write. So what I mean here is, well, these registers are constantly outputting, and they're constantly inputting into these muxes, and these muxes are going to be constantly outputting. So, I mean, while we have input in the logic here to choose which of these registers we want to output, we haven't actually controlled whether or not it's outputting, right? There's still going to be a constant output here of zeros and ones, regardless of what we do. What we essentially want to do is have a way to cut these wires completely, but control it electronically. And you can use a component known as a tristate buffer to do that. So those are just drawn like a triangle. That's not a NOT gate. A NOT gate is a buffer that's inverted. So that's why a NOT gate looks like that, and that's why a buffer just looks like a triangle, is that a triangle just means nothing. It just passes straight through. However, these tri-state buffers have a secondary input. And these essentially sort of work like AND gates, except when this side input here is just a 0, and so I'm going to take this wire here and pass it to each of the tri-state buffers. When this input is a 0 here, you can essentially just think of it as cutting the wire, right? Nothing goes across here, and that doesn't mean it sets it to 0, right? When this input is a 0 here, these are not 0. These are literally nothing. A little bit of background on that. Typically in a computer, I mean, wires are going to be represented with voltages. And when the voltage of one wire is 3.5 volts, or somewhere around there, it depends on the manufacturer, that means that this wire has a 0. And if it's 5 volts, it means it has a 1. And so here, when I mean nothing, I literally mean 0 volts, which is not a 0 or a 1. It's literally nothing. We're not putting any power here. And what that allows us to do is, if we're cutting this wire here, well, then we can still manage something on this D input here, right? We're not going to be putting zeros and ones onto these wires here. We're not going to be constantly outputting. And it essentially just allows us to control whether or not we're outputting. Then all we need to do here is recombine these all back into just a 4-bit binary bus and connect it up to the D input. And so now, if this is a 1 here, it'll actually allow this output here to pass through and go on the D bus. And that should only happen when you're reading, because if you're reading, you're not going to be inputting a value here. Because, yeah, essentially we can't be going in both directions simultaneously. We can only be going in one direction at a time. We can either input on the D bus or output on the D bus. And these tri-state buffers here just allow us to do that. So now we need a little bit more logic, right? Because we want to only be reading when the clock is 1 and this read-write signal is 0. And so we can just take these two here, bring them down here. So now we want the clock signal to be a 1, and we want the read-write signal to be 0. And so we can just do this. So now, when this read-write signal is 0 and the clock is 1, this right here will be a 1. And when we're actually supposed to be reading something, we then want to just activate these tri-state buffers and let the data through. Because remember, the address here is already just going to these muxes. So the moment you pass in an address, it's going to choose one of these registers to output to sort of this place right here. And then these tri-state buffers will control whether that output continues. Any questions on the read aspects of this? It's definitely the more complex part. If not, I mean, we're done. This is a memory component. It's going to be doing reading and writing. It's controlled by a clock, and the input and output are on the same line. If we didn't want this input and output on the same line, then we could essentially just remove these tri-state buffers, and that would work. It would constantly output. You can maybe add some AND gates or something to prevent that output from happening. But anyways, yeah, this is pretty much it. And keep in mind, I could, instead of drawing these as registers, just split them up as 4 separate D latches. And then each have, this would be my Q3 D latch, Q2 D latch, Q1, and Q0. It's just easier to think of it as a single register. And again, if you did have to break it up into a bunch of D latches, you would just take this clock signal and hook it up to every single one. I'll ask again just to make sure. Any questions on this? I do see someone typing something, so. Yeah, pretty much a tri-state buffer sort of acts like a diode that you can toggle. So it essentially, the data only will go in this direction here, and it'll only go through that if this other wire here is a 1. So I don't know exactly how tri-state buffers are actually made, but yeah, these are basically diodes that are a little bit more advanced. They have a little bit more functionality. Any other last questions on this? And then we'll go to making even larger memory components out of pre-built memory components. So here we're going to assume that we have this sort of memory component and make something larger. So let's say we're going to increase the data bus from 4 bits to 8 bits, and we're going to increase the address bus from 2 bits to 4 bits. So now we'll pack this into a chip. So we'll imagine here that this thing we can now just draw as this nice little box here with the D input / output. Then we have the address coming in from the side. We have our not read write signal, and we have the clock, which I'm just going to draw as a triangle here. So this is our component now, and we're going to use this to implement a new memory component, a larger one. And this is actually going to be easier because we already have all of this stuff here inside of this chip. So keep in mind, if you're making memory out of something like a D-latch, which constantly outputs, D-latches or registers that constantly output, you have to have this logic to control whether or not you're outputting. If you're using a memory component that already has those things inside of it, it turns out you don't need any of that input-output stuff because it's already handled here, and you'll see how that works out. So let me actually just put this in the corner here. So we have our D input now, which is 8 bits. And our address line here will be 4 bits. And keep in mind, this is going to be 2 bits here and 4 bits here. So now we have something that can hold 4 bits. So how should we go about storing 8 bits of data into things that can only store 4 bits? In other words, how many components wide should I have? Two, yeah. So what we can do is we can take the 2 upper bits of this the 4 upper bits of this 8-bit number. So let's say we're trying to write this data here. Right, we'll cut it in half. We'll take these 4 and use one memory component like this to store this part, and we'll use the other memory component to store this part. And so we'll have 2 bits wide, or 2 memory blocks wide. Okay, so I'll just mark this as 4 bits and 4 bits. So now we want to figure out how, quote unquote, tall this memory component needs to be. So keep in mind, these have 2-bit address buses. And also, so for these 2 here, we're going to connect every single control line together. So here we have the not read write, and those will be hooked up together, and the clocks will be hooked up together. The reason is the same reason when we created a register, we hooked up all the clocks together, is because if we do anything in this component, we want to mirror that in this component so that we're constantly writing either all of an 8-bit number or reading all of an 8-bit number. We're not trying to do different things with the upper and lower bits. So these 2 things have to do exactly the same thing always. Otherwise, we're sort of breaking up our 8-bit numbers and messing everything up. So now we want to figure out, again, how tall does this thing need to be? So one way to think about this is how many addresses total do we have? So we have 4 bits worth of address. So that means how many total addresses do we have? Or should we have? 2 to the 4, yeah. So again, just you have essentially 4-bit address just means you have a 4-bit binary number. And so any 4-bit binary number should be a valid address. And there are 16 4-bit binary numbers. If you were just making it like this, if you were just making it out of registers, you would just need 16 locations and then a 4-bit binary decoder. Everything would get bigger, right? You'd end up having larger muxes, right? They would go up to being larger, but yeah. So, well, this stores 4 locations, right? Each of these blocks here has 4 locations. And so how can we divide up the addresses between sets of blocks such that it makes sense? Well, if for these first 4 locations, we say that they correspond to these addresses here, well, now we can do something interesting. We can actually take the address and split it and use one part of the address to figure out which set of blocks that we're in, and the other part of the address to address within that set of blocks. You're going to so you can think of that as essentially this is a bin of 4 addresses, and we're going to need to have several of these bins. So we'll use the upper bits to figure out which bin we're in, and then the lower 2 bits to address within the bin itself. And so we'll have another set of blocks like this, and I won't draw these lines like this just for simplicity's sake. So we'll have our second set of addresses here. And so, yeah, and we'll need to have 4 of these sort of blocks here going vertically because there's 4 addresses in here. So there'd be 4 here, 4 here, 4 here, and that makes 16 total. Right? Otherwise, we won't have the 16 addresses. So we'll need 4 sets of these blocks. And yeah, so to continue this pattern here, so these are the 4 addresses that we'll assign to these. And then we'll assign 0, 1 something to these, then 1, 0 something to these, and 1, 1 something to these, right? So whatever this something is, we'll pass in as the address to this block. But if the beginning of the address is 1, 1, then that means we want to interact with this set of blocks here. And it's the same sort of idea, right? You can sort of think of this 2-bit address as being 0, 0, and then an extra thing of 0 bits. And we're using this extra thing here to address within this block. If that sounds confusing, don't worry about it. So yeah, so we'll take these lower 4 bits and wire them up as the D inputs to all of these. We'll take the upper 4 bits, wire them as the D inputs to all of these. And again, we're connecting up the address, the read-write signal, and the clock between 2 adjacent here. But I'm not going to draw all that out just because it adds some clutter. So now we need to be able to figure. We'll break apart this address here into the upper 2 bits and the lower 2 bits. And I said this backwards. So this will be the upper 2 bits coming down, and the lower 2 bits are just going to keep going up. So what we want to be able to do is look at the 2 upper bits and figure out whether we should be in this block, this block, this block, or this block. Is there a component that we know of that can go ahead and help us with that? That can go from a binary number to choosing one of these blocks here, or to basically telling us which set of blocks we want to write to. Yeah, binary decoder. Literally just take this number here, pass it into a binary decoder, and that'll tell us exactly, it'll just point to us which set of blocks we want to write to. So here we'll have a binary decoder. If it detects 0, 0, it'll output here, 0, 1, output here, 1, 0, and 1, 1. And so now we have a wire that literally tells us which of these locations we should write to. So one thing that we can do here that just will make our lives a little bit simpler is in this component we can add something known as a chip select. And a chip select essentially is just an input that allows us to enable and disable the whole component and ignore the clock. And all we have to do for that is just add it right here near the clock. So we can put an AND gate here. We'll have our clock signal and then the chip select signal. So now, in order for us to do anything with this component, the chip select has to be 1, indicating we're using this component, and the clock also has to be 1, indicating that we should be doing something, right? So we can just add that really quickly, and now we can have a chip select, which I will wire like this, which will just be like a little input on the bottom here. And so with that, what we can do is we can just take our clock signal and our not read write signal, and we'll just wire those to every single one of these components. I'm not going to draw that out because obviously that's just going to add a lot of clutter, but we're going to take the clock and the read write and just send it to every single one of these components without any sort of logic in between. And then we'll use the chip select to select which set of chips we want to write to. And again, I'm connecting these two up like this because I want to select both of these chips simultaneously. I never want to do, select this chip and this chip, for instance. That wouldn't really make any sense. Okay, so now I can just take this output of this binary decoder and just pass it directly into the chip select of all of these inputs here. Because, well, I mean, that's exactly what we want it to do. We want this binary decoder to select which set of these chips we're using. And then finally down over here. Okay, so what do we do with these upper 2 bits? Well, as we said, we're going to use, these lower 2 bits. So we use the upper 2 bits here to select between which block of memory we're using, and we're going to use the lower 2 bits to select within that. So we're just going to use these 2 bits here as the address input to every single memory block. So we're just going to straight up pass this address into each of these without modification. So the lower 2 bits just goes to every set of blocks. The upper 2 bits gets decoded and sent to all of the chip selects. Yeah, so this chip here is this thing inside of it. Each of these has essentially one of these inside of it. But yes, a chip would be a memory block. Pretty much, there's almost no distinction. There's basically no distinction between any of the terminology we'll use. Memory block, memory system, like they're all essentially the same thing. It's just all a memory component. There's no difference. There's just multiple names for it. So we're actually done. So the thing here is we don't have to deal with the reading part, right? It looks like all we've handled is the write portion, right? This essentially looks the same as the write portion, right? We don't have this AND gate here, but in fact we do, because essentially that's just the chip select here, right? That chip select gets ANDed with the clock, which is exactly what we're doing here. And the read-write signal is handled inside of these blocks. And this chip select essentially tells us which set of blocks we're using. But because each of these components internally has all this tristate buffer stuff, it's going to control whether or not these chips here are inputting or outputting. And so all we need to do is select the right block of the right, bank, and then it just works. So we're done. Any questions on this? So again, I cannot repeat myself enough. If you're asked to make a memory component that uses some sort of pre-built memory component that is just like a D-latch or a register, meaning that it constantly outputs, then you have to have this logic here to, figure out and conditionally output the thing, right? Because this is constantly outputting. However, if you're using a pre-built memory component like this to make memory, you don't have to do it because it's all internal. It's all inside of this chip here. And I mean, that's pretty much it for memory. Are there any last questions about memory? And then I'm going to talk a little bit about the actual lab and how that deals with memory and how you should be dealing with it. So the lab isn't going to actually be dealing with making these. It's going to be dealing with using memory, because it's just as important to understand how memory is used as it is, or probably even more important to understand how memory should be used rather than how it should be constructed, though it helps to understand how it should be constructed. All right.